Okay, so the way you take a derivative with the power rule is that if I have x squared, then I bring the 2 down, so I multiply the x by 2, and then I subtract 1 from the top. So that's going to be equal to 2x to the first, which is equal to 2x. If I have 4x to the fifth, then I'm going to bring the 5 down, and I'm going to get 20 times x, 5 minus 1, which is equal to 20 times x to the fourth. Okay, that's the derivative using the power rule. So if knowing this, let's start taking some derivatives using L'Hopital's rule. So if I have the limit as x approaches 3 of x squared plus x minus 12, all divided by x squared minus 2x minus 3, I normally plug in to find limits, so I'm going to get 3 squared plus 3 minus 12 divided by 3 squared minus 2 times 3 minus 3. And this is going to be equal to 9 plus 3 minus 12, which is 0. And then the bottom will be 9 minus 6 minus 3, which is going to be 0. So since I have 0 divided by 0, I am allowed to use L'Hopital's rule. And L'Hopital's rule says I take the derivative of the top and the bottom, and then I plug in my number for the limit, and I'll be okay. So let's do the same thing. I take the derivative of the top, plus 1, derivative of the bottom, 2x minus 2, take the limit, as x approaches 3, and so I plug in, so I get 3 times 2 plus 1, and then 3 times 2 minus 2, which is going to be equal to 7 over 4. Okay, that's the answer. Now let's take another limit. If I get x, the limit as x approaches negative 1, and I have x squared minus 4, divided by x squared plus x minus 12. I'll plug in, so I get negative 1 squared minus 4, negative 1 squared minus 1 minus 12, and I'll get 1 minus 3 on the top, which is going to be negative 3, and I'll get 1 minus 12 on the bottom, which is going to be negative 12, which is equal to 1 over 4. Now, notice I did not use L'Hopital's rule in this situation because when I plugged in, I did not get 0 over 0. Okay, let's get another limit going. If I have the limit as x approaches 4 from the positive side, or to the right, of 2 minus x over x minus 4, what am I going to get? So if I plug in 4 in this situation, I'll get 2 minus 4, which is perfectly okay, and I'll get 4 minus 4, which is not okay, because then 0 is on the bottom, and we do not want 0 on the bottom. So what do we do? So, from the right side, that means that our x values will be greater than 4 and approach 4, which means it'll get smaller. It'll get closer to 4, which means it'll be decreasing in value. So I might have x equal to 4.1, right? And 2 minus 4.1 divided by 4.1 minus 4 is going to be negative 2.1 divided by 0.1. And if I have 4.01, I'm going to get something very similar. I'm going to get 2 minus 4.1, or sorry, 2 minus 4.01 divided by 4.01 minus 4. And as you can see, this top number is always going to be somewhat equal to negative 2. It's not exactly equal to it, but as we take the limit, the 4.000001 becomes negligible, and it basically becomes negative 2. Now notice on the bottom, I'm going to get a very, very small number. I'm going to get 0.000 all the way until I get 1. Okay, and that's the concept of a limit. So that means I'm going to get a negative 2 on the top, and I'm going to get a really small number. And everyone knows that whenever you divide by a really small number, you get big number. Okay, and also take note that this is a negative sign, which means that this is going to be a really big negative number. So as we take the limit, this means that we're going to get negative infinity as our limit. So this is what it's equal to. Okay, so now let's take another limit. The limit as x approaches infinity of x plus 3 and x squared plus 9. Okay, so infinity is not a number. You have to know that. But if I treat infinity as a really large number, if I take it as, I'll pretend it's n, right? This number becomes n, some number n, right? N is very large. Then what am I going to get? I'm going to get a really large number plus 3, and then really large number squared plus 9, right? And so these really large numbers, n and n squared, they're the same thing. Why? Because they're so huge, I can't even imagine them. They're so huge that the difference between really large number and really large number squared has no difference. So this means I'm going to get infinity over infinity. Okay? Then the 3's and the 9's don't even matter anymore. It's such a huge number, you don't even need to pretend it's there. That's how the limit works. And since I have an infinity over infinity, you already know what that means. I'm going to use L'Hopital's rule. So now I'm going to take the derivative of x plus 3, which is going to be 1. Take the derivative of the bottom, which is 2x. And I'm going to plug in infinity. Now remember, infinity is not a number. But if infinity was a really large number, and I plugged it into the bottom, I'll get 1 divided by huge number. And 1 divided by huge number is basically equal to 0, right? 1 divided by 1,000 is really small. 1 divided by 10 million is even smaller than that. 300 million is even smaller than that. 1 trillion, tiny number, so it approaches 0. Next, let's have another limit as x approaches, maybe we'll say 2 from the left, and then let's have a piecewise function. G of x is going to be equal to 3x minus 7, where x is less than 2, where it's constant 5 when x is equal to 2, and then maybe when it's greater than 2. Okay, so it says, what is the limit of this g of x function as x approaches 2 from the negative side or from the left? So what I like to do is I like to make a number line with all the critical values. So I have a number line, and I have 2, and I have less than 2. I don't know, maybe 1, and I'll have greater than 2, which is 3. So the function here at 3 is going to be 1 minus x squared because of this condition. The function at 1 is going to be 3x minus 7 because of this condition. So what is the function going to be at x equals 2? It's going to be 5 because of this condition. So what does it mean when our x approaches 2 but never hits it? So it approaches here, but then it gets really close to it, really close to it, really close to it, but it never touches. What does that mean? It means we're still following the purple rule. We never are allowed to follow this 5 until we touch it. So that means that we have to take the limit as x approaches 2 of 3x minus 7. And this is easy, plug and chug. 3 times 2 minus 7 is equal to 6 minus 7, which is negative 1. There's your answer, okay? Let's do another problem. Let's take the limit as x approaches infinity, and maybe we'll do 2 divided by, let's do a weird number. Let's do 3 plus e to the negative x, okay? So, what are we going to do? Let's plug in infinity. So now, remember, infinity is not a real number, but we're going to treat it as is because this is a limit. So we're going to put in 2 divided by 3 plus e to the negative infinity. Maybe we'll just say negative n. N is huge, right? Now, this is not proper notation. If you see this in a math class, you should probably run from your teacher. But this is something that's really good at explaining things. Okay. So it's important to note that you look at this e to the negative n. As n grows large, then e to the negative n starts looking like e to the negative 1 over, or 1 over e to the n, right? Right. And so, if I have 1 over e to the n, what does that mean? That means that e to the n grows really large. So this means 1 over huge number. And 1 over huge number is basically 0, remember? So we can kind of replace this e to the negative n as 0. And then we have this limit as x approaches infinity of 2 over 3, basically, which is just equal to 2 over 3. Okay? This is not an indeterminate form, which means we can't use L'Hopital's rule. Okay, let's take another limit. The limit of x approaches 0 of x plus 9 minus 3 over h. What am I going to do? So whenever you see something like this with a square root, you always need to know how to do multiply by the conjugate. And so this means I'm going to multiply the top and the bottom by the same square root, but then plus 3 instead, and then divide it by the same thing, right? So we're actually multiplying by 1 technically, and this is perfectly okay to do. So now, whenever you have this on the top, you have a difference of squares. And difference of squares is kind of like x minus a times x plus a, and then you're going to get x squared minus a squared, right? So that's what a difference of squares is. Very similar to here. So you're going to have x plus 9 minus 9, right? This cancels out, and then you have this big, sorry, not h, what was I thinking? X times square root of x plus 9. Now you might think I done goofed up on the bottom, but it's okay, just wait. Okay, so now, what do we have on the bottom? So we have, oh, I see. So we have the limit as x approaches 0 of x divided by x times this big square root thingy. I should mention this is not in the square root. Okay, so now we're dividing things, so this cancels out with that. And so now you have the limit as x approaches 0 of 1 over this big square root plus 3. So now if I plug in 0, you might think, oh, it's on the denominator. No, it's not. Well, it is technically, but it's okay to do, because if I plug in 0, I'm going to get 1 divided by the square root of 0 plus 9 plus 3. This is still defined. It's not undefined. I have 0 on the bottom still. Well, I don't have 0 on the bottom technically, but I plugged it in on the bottom, and it's okay. So you always have to watch out for that. Anyway, so I have 1 divided by the square root of 9 plus 3, which is equal to 1 divided by 3 plus 3, which is equal to 1 over 6. So that's my final answer. Okay, so let's do another problem. Let's say I have the limit of limit as x approaches 0 of the sine of 1 over x. So this is, if you don't know what sine of 1 over x is, it kind of looks like this. So normal sine kind of looks like this, right? Like a wave. Well, the sine of 1 over x will oscillate more rapidly when it's closer to 0. This is 0 rapidly, and then it kind of calms down, right? So it's really dense in this middle part. So sometimes you don't even need to like algebraically maneuver this limit. You can just know that at 0 it goes like this so rapidly you don't even know where it is. Okay, and it looks like this on the outsides. And so with this, as x approaches 0, you look at it from the coming in from the right, and you look at it coming in from the left, and you see sine of 1 over x is not approaching anything. So this does not exist. Okay. Let's get another example. So it's important to be familiar with derivatives in case a limit comes up that you don't know how to solve for that needs L'Hopital's rule. So if I have x squared on the top and then I have e to the x minus 1, what am I going to do? So I guess first I'll plug in infinity, right? So I'm going to get infinity on the top because x squared is going to be huge. And I'm going to get e to the infinity minus 1, okay? And so e to the infinity doesn't really make any sense. Minus infinity minus 1. These don't even matter anymore because e grows larger than x. E to the x grows larger than x. So this is going to be infinity as well. So this is an indeterminate form, which means L'Hopital's rule rules as king. So I'm going to take the derivative of the top, and I'm going to say 2x divided by, and then the derivative of e to the x is going to be e to the x. Derivative of 1, or of x, or negative x is going to be negative 1. Okay? And so this is still an indeterminate form because if I plug in infinity for x, I'll get infinity divided by infinity. Right? So we don't want that. So we keep applying L'Hopital's rule. So we take another derivative. We go 2 divided by e to the x, because the derivative of e to the x is e to the x. And the negative 1 goes away because it's a constant. Now if I plug in infinity, I'm going to get 2 divided by a huge number. Alright? And guess what's that going to equal? That's going to equal a 0 when the limit of x approaches infinity of e to the x. That's going to equal 0. Okay?